Okay. Free energy is a force towards equilibrium, which I always think sounds like some kind of a manifesto out of the 70s. What we're talking about is how the Helmholtz or Gibbs free energies, we can look at what drives a system towards equilibrium. We've generally looked at it in terms of an increase in the entropy. But we can, I'll show you how we can actually turn that around and look at, rather than a rise in the entropy, we can look at a decrease in its free energy, which will give us an equivalent result, and could be easier in many cases. All right, so let's say that we've got a system which is in thermal contact with its environment. SYS for system. And then the environment includes not only what's surrounding it, but everything else in the universe. So we can divide the universe up very easily into a system and its environment, which means the system and everything else that's outside the system, no matter how far away. So energy can pass from the system into the environment or from the environment back into the system. And we'll be referring to the environment here as the reservoir. Because you'd agree that the rest of the universe is a pretty large heat sink, if you want to look at it that way, pretty large reservoir. Small changes in the energy exchanged with the system are not going to change the temperature of the rest of the universe. So it is a reservoir in that sense. Okay, so let's look at how we have looked at the what drives systems towards equilibrium with their environment is, between two systems, here the system and the reservoir being the two, what drives them towards thermal equilibrium is maximizing the entropy, the total entropy between the two. So let's write down the total entropy. Okay, now the notation I'm using is subscript R for the reservoir. And I will put no subscript for the system. All right, this is the entropy, by the way. S stands for entropy, not for system. So the total entropy is that of the system plus the entropy of the reservoir. So what's the change in the total entropy? Because remember, it's that increase of total entropy that the second law of thermodynamics requires. All right? Change in one plus the change in the other. What I want to do is write this in terms of the system variables. Let's see, I haven't quite gotten to that yet, though. I can turn that, put it in terms of the other thermodynamic variables. So, using the thermodynamic identity, the standard one, there's a ds in that. Okay, so recall, make sure I've got room here. The thermodynamic identity, du equals TdS minus PdV plus mu dn. I've run out of space there. Let me turn this a little. Okay. TdS minus PdV plus mu dn. Solve for ds. And then we're going to put that in here and here. Actually, we're just going to put it in for the reservoir first. So I'm going to substitute for ds in terms of all of these other things here. So ds equals, and in fact, let me subscript this with R for reservoir. So I'll use the thermodynamic identity for the reservoir. So that's some R there, some R there. There. So I'm going to divide both sides by the temperature, and then put ds on the left-hand side. And I come up with one over t du plus p over t dv minus mu over t dn. And I've subscripted everything with R for the reservoir. Now, let me make some assumptions. The system and the reservoir are in thermal contact, so they're going to have the same temperature. The system does not change size, and it does not exchange particles with the outside. So, let me see here, things I'll write down. So, T equals TR. They're in thermal equilibrium. dV. So let's see, there's no change in the volume of either the system or the reservoir. And by the way, because I've divided up the universe into system and reservoir, if one had to gain volume, the other has to lose it. So if dV is 0, dV sub R is also 0. dN, there's no exchange of particles, so dN and dN sub R are also 0. Okay, I think that will do it there. Oh, but they are exchanging energy across that boundary, separating the two. So whatever energy one gains, the other one loses. So du equals negative du sub R. Okay. Those are my assumptions here in setting this up. So, dV is 0, dV sub R is 0, dN sub R is 0, and I'm left with just these two terms. And I can put in here, let's see. I think I'll go ahead and put in that the temperature of the reservoir, TR, is the same as the temperature of the system, T. So I can put that as 1 over T. du sub R is the opposite of du, is minus 1 times du. So I can in fact put, see, these terms are 0 here, so I'm left with just that. And I can put the change in the reservoir's entropy, ds sub R, in terms of the system's variables, T and du. So that's nice then. I can put it only in terms of things that I measure about the system, and I get what the change in the reservoir's entropy is. There. Actually, I should circle this one here. That's the important thing. So, now ds sub R is negative 1 over T du. Here I've got ds. So I've got the change in the entire universe's total entropy in terms of only what happens inside the system itself. And I can just forget about the reservoir for a moment. But it was important in setting it up. All right, let me put that back in then. Let's see. So, ds total equals ds, that's the system, plus ds sub R, that's for the reservoir, negative 1 over T du. So minus 1 over T du. What if I factored out 1 over T from both terms on the right? Well, your first reaction would be to say that there's no 1 over T in front of the ds, and you're right. So, if I divide, let me see here, if I factor out 1 over T, I've got to account for it here. So if I put 1 over T there, I have to have T ds minus du. You'll see if you multiply back through here, if you distribute this, the 1 over T and the T cancel out and I'm left with ds just like I had there. And then I've got 1 over T du. Why would I factor out 1 over T? because, let's make sure that that's all clearly on the screen. TdS minus du is, sorry, I need a bit of a drum roll here, is the change in the Helmholtz free energy. Under these circumstances, anyway. Note that, we're calling that, let's see here. Okay, recall that F, the Helmholtz free energy, is U minus Ts, where we're holding T constant. Well, that's appropriate here because our setup holds the temperature constant. Then, the change in the Helmholtz free energy, dF, is du minus T ds. So that is negative of the Helmholtz free energy. I'm going to erase this little bit here so I can just go straight down. So what I've got here is negative dF. So, on the left-hand side, we have the change in the entire universe's entropy. On the right-hand side, we've got the temperature of our system and the change in the system's Helmholtz free energy. So, if thermal equilibrium is driven by, if the system is driven to thermal equilibrium with its environment by maximizing the total entropy of the universe, then, under the exchange of energy there, then it's the same as, at a fixed temperature, minimizing the system's Helmholtz free energy. We can put what goes on in the entire universe in a limited sense in terms of what happens inside the system in a more limited sense. Interesting, isn't it? So, maximizing that means minimizing this. But here, we can just look at what goes on inside the system. And because we know it's in thermal equilibrium with its environment, which is taken care of by having the temperature fixed, we don't have to worry about the rest of the environment in doing this. Okay. So, increasing that means, because of the negative sign, decreasing F. All right, the system will do whatever it can to minimize its Helmholtz free energy. Okay. Well, in this case, what I had done was to hold the temperature fixed and to hold the volume fixed and the number of particles fixed, and I just let the temperature was fixed because it was we were letting it be in thermal contact with the environment. And so you had an exchange of energy across the boundary. So du was negative du sub r. The change in the system's energy was negative of the environment's energy. What if there's also the ability for the system to expand and contract? So we can exchange, in a sense, we can exchange volume with the environment. As it exchanges energy, it can also exchange volume. It can expand. Okay. This is appropriate, again, when, let me see here, temperature, volume, and number are constant. That's when we can use this here. Now let's see if we hold only temperature and number constant and allow the volume to vary. let's see here. So now, we're going to allow the pressure to stay constant and the same as the reservoir. So T equals TR. P, pressure, equals the pressure of the reservoir. And we're going to have whatever energy the system gains is energy the reservoir has lost. Whatever volume the system gains is volume the reservoir has lost. Okay. If we do that, now we have one more variable to handle. So here, here's our system. Here's the environment, the reservoir surrounding it. It can exchange heat with the environment, thermal energy, and it can exchange volume. So imagine that we've got a cylinder here with a sliding piston that can move in and out. Simple way of modeling that. Okay, and then the reservoir is what's surrounding that, everything else in the universe. But we still have no exchange of particles, so dN equals dN sub r equals 0. Okay. So now we are in thermal and mechanical equilibrium. Mechanical equilibrium is this sliding of piston, volume change. In that case, just as before, we look at it in terms of the change in the universe's total entropy. This is the change in the system's entropy plus the change in the reservoir's entropy. For the reservoir, we use the first law, the thermodynamic identity, du, and I'm subscripting all of these with an R, equals TdS minus PdV plus mu dN. I think that just made it on there. Subscript R. Okay, dN is 0. So I've got these two terms on the right plus the du. Once again, solving for ds sub r. So I've got to divide both sides by t. Find my place here. There we go. As before, du equals negative du sub r. T equals tr. And here now we're going to have the pressure, it's in mechanical equilibrium, so the pressure of the system is the same as the pressure of the reservoir, so P equals PR. dV equals negative dVr. Again, whatever the system gains, the reservoir loses. So I can rewrite this in terms of the system variables. I've got a negative sign here, so minus 1 over T du. Let's see here. Whatever the system gains in volume, the reservoir loses, so I've got a minus sign here as well. Minus P over T dV. Yes, that's good there. Put that back in. Let's factor out a 1 over t once again. In fact, let's factor out a negative 1 over t. Make life a little bit easier. let's see. Oh. Yeah. And I'm going to change the order slightly here. Order. I'll have, so minus 1 over t times, parentheses, du minus TdS plus PdV. Why did I pick that? Because that is, if you take the definition of the Gibbs free energy, what we wind up with when you take the differential, so PG, it's just that. So in this case, if we allow both temperature, thermal equilibrium and mechanical equilibrium, so the temperatures are the same, the pressures are the same, which means that the energies can be exchanged and the volumes can be exchanged, then we wind up with the idea that increasing the total entropy of the universe is the same as the constant temperature you see here, decreasing, negative sign, the system's Gibbs free energy. So this is useful when, let's see here, our pressure and temperature and number because we haven't exchanged any particles, are a constant. Just drop my page there. T, P, and N. Yes. Okay. So under those conditions, a system's Gibbs free energy tends to decrease. All right. So a summary then. Space. Okay, summary. At constant energy, volume, and number for a system, the entropy, parameter of entropy, tends to increase. At constant temperature, volume, and number, the Helmholtz free energy tends to decrease. And at constant temperature, pressure, and number, the Gibbs free energy tends to decrease. So, that tells you under what circumstances you're dealing with, what you can say about one of these three parameters describing the system. So here's the thing. Another thing. Looking at these, it seems almost arbitrary how we're picking which variables we're holding constant, which ones we're allowing to vary. There's a real mishmash of what's constant, what's variable, and it doesn't seem to have much of a system to it. Although you can certainly pick things in a given situation, you can tell which one's constant, which one's not. How can we think more clearly about which ones might be changing, which ones might not be? That brings us to the idea of extensive and intensive quantities. What we're going to be dealing with is if you were to, say, double the system, make an identical copy of it, put the two together, what's going to change and what's going to stay the same under those circumstances? Go back over here. Extensive versus intensive. All right. If you were to, and this is the way the book words it, which is probably the least complicated way to think of it. Let's say you've got a system here, and it has things you can measure about it. It has entropy, it has volume, it has number of particles, it has mass, it has density, pressure, energy, Helmholtz free energy, and so on like this. Now, take a system, wave your magic wand, and make an identical copy of it. Everything about this is now the same true about that. Now what I want you to do is if this is identical to that, what happens when you compare the total, the two of them together, to just the one? What changes and what stays the same? For example, some things you know are going to change. Whatever the total mass, whatever the mass is of part 1, part 2 has the same mass there, so the total is obviously twice the original. But what about the temperature? Temperature is a different kind of a thing. Temperature is involved with energy, kinetic energy per particle. So the temperature here is the same as the temperature there. The total, you don't add the two temperatures together. It's the same throughout the whole thing. If your temperature within this room is the same everywhere, and you put a divider down the middle, the total temperature of the room is not the temperature of one side plus that of the other. It's just the same on both sides. So this is our idea of extensive and intensive quantities. Extensive ones are the ones which double when the system is doubled this way. Intensive ones are ones which stay the same when the system is doubled. So, it doesn't have to be just doubled. It could be tripled or quadrupled or halved or whatever. Extensive ones include volume, number, entropy, energy, enthalpy, Helmholtz free energy, Gibbs free energy, and mass. I'm not writing a letter for the mass because we have capital and lowercase m's and so on. Mass. Intensive quantities are ones which stay the same when you double the system and consider both parts together. For example, so let's see here. Stay the same when system is doubled. For example, temperature, pressure, chemical potential, interesting, and the density. What are the different qualities of things in these two categories here? Well, you'll notice that you're used to adding extensive quantities to each other. These are things which, when you consider one system plus another system considered together, the total volume is the volume of one plus the volume of the other. The total mass is the mass of one plus the mass of the other. The total energy, one plus the other. Entropy, we need to add those as well. Intensive quantities, you don't come across many situations where you'd be adding. You don't add the temperature of one to the temperature of the other. Temperature is, with some scale factors in there for the units, energy per particle. It's already a ratio. It's something per something else. Pressure, our most basic definition of it is force per area. So when you double the system, you're also not only doubling the forces in there, you're doubling the area that they act over, and those cancel out. The temperature, scaled kinetic energy per particle, well, if you double the system, you're doubling the energy involved, but you're also doubling the number of particles. So one over the other, that scale factor cancels out. Same thing with density, mass per volume. You double the mass and you double the volume, so those cancel out, the density stays the same. Chemical potential is a bit trickier, but I'm going to get to showing you how that comes out in the same kind of way when you think of it right. We just don't really have an instinctive, everyday feel for chemical potential. Okay, there are rules, mathematical rules, for what you can do with extensive quantities and what you can do with intensive quantities. Let me put some space up for those. Okay, so here. The rules. Extensive times, let's see here, intensive yields an extensive quantity. Extensive times intensive yields intensive. Yields extensive. I've got to keep looking in one place and not both. Example. Oh boy, I better not write EX for example then, should I? Example. Volume times density equals mass. Density is mass per volume, so volume times density equals mass. Volume is extensive, put that on this. Density is intensive, and you multiply the two, you get an extensive one, mass. Okay? If you divide an extensive quantity by another extensive one, you get an intensive. For example, mass divided by volume, this is extensive, that's extensive, gives you density, which is intensive. So these densities, many of them we already know are ratios of extensive quantities, as I was saying a minute ago. Okay, if you multiply extensive times extensive, you get something that's neither. And he makes a note that if you wind up in a calculation trying to multiply an extensive quantity by another extensive one, there is a good chance you're doing something wrong. Now, it doesn't rule that out, for all space and time and all possibilities of any calculation, but good chance you're not going to come across that. For example, I mean, what are you going to multiply volume by number, for example? You might divide number per volume and you get, population space and so on, but not really going to be multiplying them. Okay. If you add two quantities of the same type, you get another quantity of the same type. So, extensive plus extensive yields extensive. Intensive plus intensive yields intensive. And he gives an example just of the former. For example, enthalpy is defined as energy plus pressure times volume. That's extensive. That's extensive. What's pressure times volume? Well, pressure, you have to go back to the previous screen. Pressure is intensive. Volume is extensive. Intensive times extensive gives you extensive. So PV is extensive. So that's intensive, pressure. That's extensive, volume. The two of them together give you an extensive. Extensive plus extensive gives you extensive. Nice. All right, there's a great example unifying several of these rules here. If you were to add extensive plus intensive, you can't. That's not allowed. And he says, for example, EXANPLE, always want to abbreviate it, you cannot add, you will never come across Gibbs free energy plus chemical potential. What are the units of Gibbs free energy? Well, I mean, it's what kind of quantity? Of course, it's extensive. It's energy, right? Units of energy in joules in general. Chemical potential is also in units of energy. So our dimensions work out perfectly fine. Energy plus energy. Doesn't mean anything. Despite the fact, dimensionally, it's perfectly fine, it doesn't have any physical meaning. Okay. You can exponentiate an extensive quantity, and then you wind up getting something which, he says, is multiplicative rather than additive. So, I mean, we're used to adding extensive quantities together. I mean, the total entropy of the system is the entropy of one plus the entropy of another. But if you exponentiate it here, what about e to the exponentiate the entropy? Well, to get the units to work out, because we have to have, we can't exponentiate something that has units. We would divide by the Boltzmann constant. That's the multiplicity. We have exponentiated an extensive quantity right there, and the constant is just a constant. This is okay. But what happens when we've exponentiated that? Well, now, what do we know about the multiplicity of one system and the multiplicity of another? We don't add those together, we multiply them together. Whereas the entropy total is the entropy of the one plus the entropy of the other. This is what he means by a multiplicative term. The entropies add, but the exponentials of those entropies multiply. Okay. I think that does pretty well on that part there. In time remaining, I want to cover the last section of 5.2, which gives the uses this discussion of intensive and extensive quantities to get us a better understanding of what the chemical potential really is. I said in an earlier lecture that chemical potential is roughly the amount of energy carried into the system for every particle you add to it. But we've got to be careful about under what circumstances that is the case. And what else is the system doing while we add in particles there? Because we may have entropy changing, we may have volume, things like this, temperature. So what can we say about what happens when you add in a particle? Okay, if you look back to, I believe it was in the last lecture, where using the thermodynamic identity for the Gibbs free energy, I had derived an expression for the chemical potential in terms of the change in the Gibbs. This is a partial derivative. The change in the Gibbs free energy with respect to particle number. So while we hold temperature and pressure constant, that's a key thing. That means that we are in maintaining thermal equilibrium with our reservoir and mechanical equilibrium with it. So, for every, the chemical potential under those circumstances of T and P constant is how much Gibbs free energy is brought into the system with the addition of every new particle. Now notice here that both temperature and pressure are what kind of quantities? They're both intensive, right? Okay. And we also have that Gibbs free energy and number are both extensive. So extensive divided by extensive gives you intensive. So the chemical potential is intensive, despite the fact it's got the same units as energy, which this does too. Well, particle number has no units. It's dimensionless. It's just a number. So that's one reason why we have an extensive thing here in units of energy, but an intensive one here. Mu behaves a little differently. So you add one particle to the system, holding the temperature and the pressure fixed, you wind up increasing the system's energy, Gibbs free energy, by mu. That's how much energy, Gibbs free energy, each particle brings in. And he points out, and here I'll just admittedly read from the book, as you keep adding particles in, if you do this, here's your system. Bring a particle in, increase its Gibbs free energy by mu, bring another one in, and so on. That's how much Gibbs free energy mu is how much Gibbs free energy it brings in. You might think that when you do this, as you bring in a lot of these particles, the value of the chemical potential might gradually change, so that by the time you have, say, double the number of particles in the system, that you might wind up with adding in a mu that's very different from what you started with. But he says, if temperature and pressure are held fixed, this can't happen, because each additional particle must add exactly the same amount to the Gibbs free energy, because G is extensive. G must, if you double the system, G must be doubled as well. And the constant of proportionality between the number of particles in the system and the Gibbs free energy is mu itself. according to this equation here. If you start off with none, and then if you start off from 0, and you keep building it up, you keep building up the Gibbs free energy, one particle at a time, each one brings in chemical potential mu. So mu is just the Gibbs free energy per particle. And this is a nice way of thinking about it. Now, this was not the only expression we had for the chemical potential. For example, I did the same derivation for the Helmholtz free energy, F. So let me make some room here. Okay, that ought to get me both of them over there. In the language of our English professors, compare and contrast, when we start with, from the Helmholtz free energy, F, and I derived an expression for mu, which was that it was the change in the Helmholtz free energy with particle number when you hold temperature and volume fixed. Okay, again, perfectly valid, entirely correct. So if we hold the temperature the same and we hold the volume the same, we keep adding in one particle after another, then we would have the chemical potential is the change in the system's Helmholtz free energy, F, with each additional particle. How do we hold the volume the same as we keep adding in particles, though? Well, you do that, then something else has to give. The temperature being the same is one thing. Temperature is intensive. But the volume is extensive. So as you double the number of particles in the system, you're doubling the volume. Or if you held it constant, you'd have to change the density, the pressure, something else like that. If you do that, then your chemical potential will be changing. So under these circumstances, you don't have the same chemical potential as you scale up the system. And so you don't have something that is the same for the first particle as it is for the last particle. Mu will change under the circumstances of constant temperature and constant volume. So this is not the right way to intuitively understand it. It's perfectly correct, but it is less physically useful in expression. Okay. Let's see. Yeah. So we're trying to hold both an intensive quantity and an extensive quantity constant at the same time while we increase the system. And that's just physically not a good way to work for it. Okay. I'm not going to cross that out because this is a correct relation, just physically less important. Looking back to this here, though, with the Gibbs free energy, if we have more than one kind of particle, then more than one species of particle. Let's say we've got hydrogen and oxygen. We're pulling in individual hydrogen and oxygen atoms, or something else maybe that won't react. Then for each species of particle, each different kind of atom or molecule, I'll subscript it here, instead of just G being in mu, if I've got two different kinds of particles, well, I've got the number of the first one times that one's chemical potential, say helium, plus the number of the second one, say oxygen, and its chemical potential, plus, well, same thing for every other type of particle, species of particle. So in general. And I can always express this with the summation symbol, which is a nice compact way of doing it, where I just sum over whatever label or index I'm putting there. I'm going to put I for index. Okay. He says this result does not imply that the Gibbs free energy for a mixture is equal to the sum of the Gibbs free energies of each of the individual pure components, because the chemical potentials here are generally different when you're in a mixture than they are when you have a pure substance. If your system is nothing but helium atoms, you can calculate, or you could look up, find the chemical potential for those helium atoms. But if you've got a mixture of helium and oxygen, say, the chemical potential for the helium atoms in this mixture is generally different than it was if it was helium alone. All right. And as an application, we're going to derive a general formula for chemical potential of an ideal gas. And I will end up with that. Okay. We consider amount of gas at a fixed temperature, and we're going to vary the pressure. So, by equation 5.35, which is G equals N mu, and he says 5.24, but that's not really as obvious. Let me see here if he'd actually made a mistake. 5.24 is, it's definitions of chemical. One thing he's got is definition of chemical potential. Mu equals dG by dN with T and P held constant. Let's see here. He doesn't do this derivation, and I'm going to at least do a bit on it here. Okay. So, let's see here. Let me divide. We put mu, therefore, is equal to G over N. I'm going to take the differential of both sides. I'm going to divide both of these by the differential of the pressure. And I'll make that a partial derivative. So, partial of mu with respect to P equals partial of G over N with respect to P. Okay. If I hold, let's see, a fixed amount of gas, so the number is constant, I can pull that outside. Okay. And let me see here. 5.24, kind of a mysterious reference. Here we go. The thing is, there were three equations in 5.24, back on page 157. This is the one he means. Volume is dG by dP when temperature and number are held constant. dG by dP is volume. Cool. Okay, so what does that get us? Well, if you remember the ideal gas law, which you do, PV equals NKT. So if we have V over N, I divide both sides by N and by P, I've got KT over P. V over N is KT over P. Ideal gas law, that's that there. So, let's see if this actually makes some sense. Yes! That's what I've got there. All right. Now, what I've gotten up to is sort of between his equation 5.38 and 5.39. All right, what are we going to do with this? If I were to, I've got a partial derivative, I can put, let's see here, P, all right. I want to get all the p's on one side and everything else on the other. This is called separating the variables. And it's a technique in partial differential equations, which you don't need to have for this, but think about this. I've got a partial derivative here and other things here, but this is a change in pressure, and that's the pressure at some given moment. So put it this way here. Multiply both sides by dP, divide both sides by kT, and I will have d mu times, let's see here, let's put 1 over kT times d mu equals, and I'll have here dP over P. I think that's right. What would I do with this? Well, if you have a differential on both sides, the logical thing to do is to integrate both sides, to get rid of that. So integrate, and on the right-hand side, we'll integrate from some initial pressure P with a superscript 0 up to a final pressure P. And on the right, now he describes this, I think, poorly from a mathematical sense. He says integrate both sides here from P naught up to P. Well, here we're going to integrate over mu, though. So we're going to have it from mu with a superscript 0 up to final mu, where the chemical potential 0 corresponds to the circumstances where you're under this starting pressure. K and T are both constant. We're dealing with constant temperature, and K is a constant anyway. We don't have anything to worry about here. So we can pull this outside the integral, and the integral of d mu is just mu. Well, it's mu final minus mu initial. So, there. Integral of d mu is mu minus, it's delta mu, change in mu. Final minus initial. On the right-hand side, we've got the integral of 1 over the variable. Well, the integral of that is the natural log of the variable. So here we get natural log of P, but it's natural log of P final minus natural log of P initial, which gives us natural log of P final over P initial. Superscript 0 in it. Okay, so what can we do with this? To simplify it, what we want to do is we want to solve for that final chemical potential in terms of the starting things, in terms of everything else. All right, so I'll just take this term here. I'm going to multiply both sides by kT. That'll be the easiest. I'm worn down to the nub of this thing. Okay. Good. I came up with exactly what he had. All right. what this means is the chemical potential at a given, let me put it in somewhat clearer terms, at a given temperature and pressure is equal to some reference chemical potential at that temperature plus kT times the natural log of your given pressure divided by some reference pressure. So P superscript 0 is a reference pressure, usually atmospheric pressure. Okay, so generally put as 1 bar, usually, but it could be something else. Could be any reference pressure you want to put in. And then the corresponding chemical potential at that reference pressure, look up in tables. So this tells you how the chemical potential varies as the pressure or the density changes. And if you have reading from the book here, if you have a mixture of ideal gases, several different ones, then this equation applies to each of those ideal gases, each of the species separately. But what you've got to do then is to take P here to be what's called the partial pressure of that species. And there's a homework problem earlier on page 120, where partial pressure is defined. Now this is going to be kind of hard to see out here. So again, if we're adding up the chemical potential times the number, G equals N sub 1, mu sub 1 plus N2 mu 2 plus N3 mu 3, and so on, for a mixture of ideal gases, then the mu that we can use for each of these is this equation, but where P is not the pressure of the whole system, it's the fraction of that pressure that this species is responsible for, called the partial pressure. And we would put in P sub I is the partial pressure of that species, and it's defined as the number of particles of that species in our system divided by the total number of particles in the system, I'll put subscript total, times the pressure of the whole system. This is the partial pressure. And that's what you would put in here if you had a mixture. And he says, this works because ideal gases are mostly empty space. They're not crowded. There's a lot of empty space for them to fit in. How an ideal gas exchanges particles with the environment isn't affected by the presence of another ideal gas. You put the two of them together, and what had been a small number of particles in a large volume is still a small number of particles in a large volume. If you ever got to where they were feeling crowded, you'd no longer be dealing with an ideal gas. And we'd have to go on to very dense systems, which are in later chapters. Okay, and I will end here.